Hello, my name is Daniel West, and this is my EE501 project, where I use a frequency modulated continuous wave, multiple input, multiple output, software defined radio radar to wirelessly transmit range information. This system uses dual software defined radio architecture to perform distance estimation through the reflection of a chirp signal. One software-defined radio is responsible for transmission and the other is dedicated for reception. The separate modules are synchronized using a shared reference clock and trigger. The use of a 2x2 array allows for spatial diversity, which is necessary for determining the angle of arrival. Although this project is capable of determining the angle of arrival using the music algorithm, this report only covers range estimations in the time and frequency domain. A separate advantage to using multiple antennas is it simply directs and detects more of the signal. The radar transmits a single chirp that increases in frequency with time. Although redundant, viewing the waveform in the real sinusoidal form rather than the complex exponential, it's slightly easier to view what's going on. We can see that the instantaneous phase angle theta of the chirp already has the natural frequency defined within it as 2 pi f, but also increases with the chirp slope mu, which is dependent on the bandwidth and duration of the chirp. The transmitted signal reaches the target and is reflected back towards the source. Once the signal reaches the receiver, the signal has information pertaining to the range of the target encoded as a propagation delay. Looking at the equation for the received signal, notice that it is attenuated, delayed, and for a moving object is Doppler shifted, although for this project we assume a static target. Using the product to sum identity as an example, we can see that mixing the transmit and receive signals produces a high frequency component and a lower frequency beat component. Looking at figure 3, notice the bottom plot, the high frequency component in green and the lower frequency component in blue. The lower one is key because it provides the time delay due to overall distance. Since we're only concerned with the lower component beat signal, then the product of the transmit signal and the conjugate of the receive signal can be used to obtain only the lower component beat signal. Performing an FFT on this product reveals the beat frequency, which is directly proportional to the round-trip time delay. The radar system is controlled through a custom graphical user interface made using MATLAB App Designer. This helps streamline the entire process through 4 buttons: Generate Chirp, Master, Slave, and Post-Processing. The Generate Chirp button creates the waveform using a custom function and saves it to SC16Q11 format for transmission. The Master button launches a Blade RF command line interface script that configures the master software-defined radio. This includes setting the frequency, sample rate, bandwidth, gain, and enabling the reference clock and initializing the trigger input. The Slave button provides nearly identical configuration for the Slave software-defined radio. with the only exception being that it arms the trigger. So once the command is provided from the master terminal, then the master transmits while the slave receives simultaneously. Data is then saved to RAM in the SC16Q11 format. Finally, the post-processing button performs signal analysis, including delay estimation and beat frequency extraction using the saved, transmit, and received SC16Q11 files. The graphic user interface displays time and frequency domain plots, start indices, and a heat map for visual representation. It also allows system delay offset compensation input from a text field. The link to the GitHub repository is included in the link. The components used in the project can be viewed in the table. The entire system cost about $2,000. I was able to secure funding from the Resource Budget Committee, which greatly decreased my cost. The key contributions include the implementation of the RAM disk to store waveform files, which improved latency issues. I adapted the SC16Q11 storage functions that was provided by Nuon, who manufacture the Blade RF software-defined radio, and I modified them to support dual-channel MIMO functionality. The MATLAB digital signal processing algorithm was developed and provided coarse and upsampled delay estimation using cross-correlation, as well as beat frequency analysis and angle of arrival estimation using the music algorithm. Finally, a graphical user interface is created to help streamline the cumbersome process. Hello, this is software-defined radio radar. Uh, you'll notice that the antennas are not connected to the software-defined radio, and instead it is set up to do loopback testing of a 1-foot piece of RG316 coaxial cable. And you'll notice that there's two 10 dB attenuators, and that's to help protect the front end of the receiver. Also, there is this wire connecting the two, and that acts as a trigger. So in software, I could send one command to this master module and it will transmit and receive at the same time. On the right, we have a GPS discipline oscillator, and so what that does is this is the antenna, and it receives a signal from a GPS satellite, and it outputs two 10 megahertz reference clocks to both software-defined radio's internal clock, and that helps with frequency stability. If we were not using the GPS discipline oscillator, in software I might say for the master module to read 2.4 gigahertz, and that could be off. And then this one, I could also say 2.4 gigahertz, and then that'll be off, which will give us a lot of errors. So it helps just keep them both synchronized. I'm using my desktop computer. Both software-defined radios are connected to USB 3.0 for better latency, and then the GPS discipline oscillator is just hooked up to the USB 2.0, mainly to just power it. So before we get started, I pulled up a propagation delay calculator. A 1-foot section of RG316 should have a cable propagation of 1.47 nanoseconds, which is really small time delay. So I created a graphical user interface and it uses four buttons, and each one of these buttons calls back to the code for the user interface. And so here's the code. There's a lot of custom functions, and instead of going in detail for everything, it is available on my GitHub account, but I'll kind of go through this. So the first button is the generate waveform. It sets the name of transmit file, and it's taking it from digital RAM. And then it calls generate chirp waveform function. So the generate chirp waveform function is a custom function that just sets the parameters: start frequency, end frequency, carrier signal, the chirp slope, and it turns it into a 2-channel chirp. So it's setting it for both channels, and then you'll notice that it saves it to a SC16Q11 file. That's another custom function that takes an IQ signal and saves it as a SC16Q11 format. So going back, now the second button is the run master button, and so that button literally just runs a master script, and the master script runs a bat file. And so the reason that I had to do that is because from MATLAB you can't open up a separate program from MATLAB, so I had to
create a function to run a Windows batch file, and then the Windows batch file, let's see, where is that Windows batch file? Oh, master bat. This starts Blade RF command line interface. And so that's the program, like a terminal that controls the software defined radio. And it opens up the master based on the serial number, and then it runs a script within Blade command line interface. And that script just sets all the parameters, right? So the carrier frequency, sample rate, bandwidth. Notice that the sample rate is twice the bandwidth, and so that's Shannon-Nyquist theorem. It sets the bias T's, which right now they're off. We can set the gain. We configure where the file is coming from. So the file we're using is a transmit file, which is saved in digital RAM. And then we apply the reference clock for 10 megahertz. And we're using an onboard clock. And then it arms the trigger. Okay. So now we do a similar thing for the run slave button. It runs a slave script. And the slave script does it nearly the same exact thing, except for it arms the trigger of the slave, and then it's waiting for the trigger to be sent. So rather than going through all of that, that's just a basic explanation of what the slave script does. And then we do the post-process button. So by this time, we have a transmit and a receive file. We set a system delay, so that's like it offsets the inherent hardware delays, and then we run the process radar data function. Process radar data function has all the same parameters that were set in the software defined radio. It loads the signals and saves them to variables. We do cross correlation of the signals to get the time delay, and then we do upsampling using interpolation to get a higher resolution time delay sample. And then we calculate the time delay in the time domain, and then we calculate the range in the time domain. We use cross correlation to get the time delay, and then we calculate it in the time domain. And then we mix the signals. So we mix the transmit signal with the conjugate of the receive signal to get the beat frequency. Using the beat frequency, we do a FFT, and then the FFT, we're able to extract the time delay and calculate the range. So we're able to do that with the beat frequency without the need of cross correlation. So in the graphical user interface, we'll see that both of them are available. Like right here, we'll show the output of the time domain and the frequency domain. We take the average of the two just to kind of see how agreeable they are. With such a small propagation delay, this is kind of pushing the system to the limits, and we're just kind of comparing to see how agreeable they are. So from previous attempts, I know that the start index typically starts at 42. Since we're doing a 1 foot cable, we're just going to set the start index to start the system delay offset to the start index. So we're just going to measure that last little bit of propagation delay. So let's go ahead and press the buttons. So we generated the chirp. It is being saved in our random access memory. We can see this is an up chirp. Now we're running the master script. So it's plugging all the parameters into the software-defined radio. We can see there's a blinky light on the master module. Okay, master script executed. Now we run the slave script. Okay, so now it's doing, now the slave module's blinking. Okay, ready. Fire the trigger on the master device. Go back to the master command line interface. I set the code in that description, so it just needs to be copied and pasted. We run it. So now it transmitted and received in that instant. Now I'm just going to exit both command prompts, and then we can do post-processing. Okay, so we can see that the start alignment was actually 41. Occasionally these, sometimes they're identical and sometimes they're off by one sample. So I'm just going to set the system delay to 41 and do post-processing again. Okay, so what I see are two FFTs. We can see that there's slight attenuation on the higher frequencies, but both of them have similar results. I've noticed with this system occasionally one of them will have really good results and no attenuation, and when that happens the other one will just completely destroy the upper end. So it seems like a lot of times that there's like a dependent channel, but if they can align up like this, that's the best. So then in the time domain, what we see is this is the information is coded in here of the distance to the target, or for us it's just the propagation delay of that 1 foot cable. And so the system delay that we entered, this 42, it just helps get rid of some of that, because there's an inherent delay from the hardware through that trigger cable, through the GPIO pin. And then this is the beat signal, and we could see it's really small. Let's see if we can zoom in on it. Yeah, I mean, I think that would be like 9.76 kilohertz. And then moving over, these are the results we got. So in the time domain, using cross correlation, we got a delay that was 2.65 nanoseconds, which gave us a range of 1.3 feet. And then in the frequency domain, we had a delay of 4.08 nanoseconds and a range of 2.0 feet. And then taking the average of the two, we get 1.65 feet. And then the plot, you can see it's right here, and I'll zoom in on it. And there's actually 3 samples here: the time domain, the frequency domain, and then the average of the two. And so that's why it's kind of spread out. So not completely identical results, but we are literally trying to measure 1 nanosecond. So this is the software-defined radio radar, and we have a target that it was measured at 40 feet. We have a transmit antenna array that is pointed directly at the target. We have 2 bandpass filters with the center frequency of 2.45 gigahertz and a bandwidth of 100 megahertz. On the left is the master, and on the right is the slave. The master sends out the waveform, and this cable connects the two through a GPIO pins, and it triggers both devices at the same time. So the transmit and receive happen simultaneously. We're using 2 power amplifiers on the transmit side, 2 low noise amplifiers on the receiver side, and we have the receive antennas. And this is a GPS reference clock, and the antenna for the reference clock is over here, and it is locked onto a satellite, and you could tell that it is locked because there's 2 red lights that are solid, and you can see that that is sending a signal to both software-defined radios to help with them being frequency aligned. I want to point out that because of the amplifiers, both the master and slave are both using external power. And I do have a air-to-ground radio. You could probably hear the airplane flying around, and it's on. I'm using a completely different frequency than the amplitude modulated air-to-ground radio. The radio's out here mainly to ensure that there's no interference, which there isn't. This is the graphical user interface. And the way it works is you generate a chirp, and we can see it's a 10 microsecond chirp that increases in frequency. So by generating the chirp, we create the SC16Q11 file. It's a binary file for saving IQ signals. And then we can run the master script, which we can see that the light is starting to run on the master module. So this sets the center frequency, bandwidth, gain, locks onto the reference oscillator, and it's initializing the trigger. So now it's saying to run the slave script. So we're gonna go to step 3 and run the slave script. So this does this similar thing, sets the center frequency, bandwidth, sets the clock reference, and then it's waiting for the trigger. So now we go back to the master script, and this is the command that needs to be applied. So I just copy, paste it, and then I press enter, and it transmits and receives simultaneously. And we could see that as soon as I press it, both of them okay, just exiting both terminals, gonna okay that. And then now we just press step 4, which is post-processing, which this graphical user interface will end up populating with plots. Okay, post-processing complete. And usually takes a couple seconds for this to populate. So we can see the receive signal. We can see the receive signal for channel 1 is on the left column. The receive signal for channel 2 is on the right column. And it looks like there's some noise, but we can see this delay. There's a slight delay, and that is the distance that is encoded being reflected back from the target being captured on this receive array. And looking at the beat frequency, we can see that it is slightly shifted to the right. It's about 253.9 kilohertz. So then in the time domain, so using the time delay directly and computing the distance, we get 41.94 feet. Now using the frequency domain, we get a slightly more accurate result of 39.9 feet. And then I'm just taking the average of the two, is 40.92 feet. And this is the range versus angle of arrival heat map. We have angle of arrival on the bottom, the x-axis, and the range on the left axis. So it's slightly shifted to the left, but we're right about 40 feet. And this is actually plotting the time. It's plotting the time domain and the frequency domain and the average. So it shows up as a single plot. But if we were to zoom in, which I'm trying to zoom in right now, but there we go. If we zoom in, it'll show up, kind of shows up as 3 of them, but there's 3 of them there, and then they kind of intersect to create a elongated signal. So this is a way to see how agreeable the time domain and the frequency domain are with this method. So we could run it again, but we're already about 8 minutes into the video. But I think though that's a pretty decent result. 40.92 feet. And that is 40 feet. Thank you.
So there were several noise reduction methods used in this project that wasn't directly for reducing the noise of transmitting and receiving, such as using the GPS discipline oscillator. That helped to overcome clock drift and inconsistent phase alignment between the master and slave modules. Also, the RAM disk was used to reduce latency issues that had to do with the startup time. Also, there was bandpass filtering, and that was specifically to comply with FCC regulations. And there were gain stages used, power amplifiers, low noise amplifiers, and that would help boost the signal to noise ratio. And then lastly, the system delay compensation, and that helped to correct for fixed hardware issues, the trigger latency issues. I feel that the proposal aligned really well with the overall implementation. Um, I would say that the only exception is that in the proposal, I described testing that would be 20 feet, 40 feet, 60 feet, etc. And for this project, all I did was demonstrate a 1 foot coaxial loopback test and a 40-foot over the air demonstration. Although numerous tests were performed, um, there was only time to demonstrate those two things. The radar system achieved consistent range estimates, and although there was a handful of challenges during this project, specifically related to latency and synchronization issues, the majority of them have been overcome. Using the reference clock for frequency and phase alignment, as well as the RAM disk for waveform storage, has provided stable results. And although a hardware latency issue is still present, the use of the system delay compensation still allowed for accurate range results. There is much more that can be done on this project, and in continuing research, I would be most interested in eliminating the need for the system delay compensation. One method to overcome this could be to provide two sequential captures, one as a reference signal to align the phase offset between modules and the other for the digital signal processing algorithm. I am most interested in integrating frequency hopping capabilities into the waveform and begin experimenting with dual function radar communication.